live on my way to Mars on a collision course. I am a satellite. I'm out of control. I'm alone in the family of the sun. Curiosity tasting everyone on a home. There's some from the sun. Out of the silent planet come the demons of creation. The ocean plummeted from birth.
So I'm muscly and everything. How's space?
Hello everyone and welcome to this week's lecture, Exploring the Outer Solar System. I hope by now you've picked up that by the outer solar system we mean everything beyond the main asteroid belt and out to, well, the edge of the solar system as we know it. Now, while many of the unknowns of outer space tend to be located outside of our solar system, there is a direct relationship between distance from the Earth and knowledge of the physical universe, as you might expect. That is to say, the further we get away from Earth, well, the less we know. One question we have only discussed a little bit in weeks 2 and 3 is, where does the solar system end? Well, that's a good question, and it's analogous to the question of where does the Earth end and where does space start, in that there are a few different answers. Some people point to the extent of the sun's light, others to the sun's gravity, and some focus on the remainders of that old protoplanetary disk we talked about at the beginning of the course. For us, it's not really that important where the solar system ends, given that it is extremely likely any of us will ever see a spacecraft reach another solar system. That's something that could be measured much more obviously. And given that it's a near certainty that humans will probably never travel much further than, well, Mars, or if even that far, for any extended period of time. Our main concern in this class is how far we have explored and how far we could explore, either human or robotic. The answer is probably somewhere in the Kuiper Belt, which I hope you're familiar with, again, from weeks 1 and 2. Sure, robotic spacecraft will probably one day reach other solar systems, but by then, after such a long journey, I'm doubtful there'd be much left of them to send data back. In this video, we're going to focus exclusively on the gas giants. So while this is called exploration of the outer solar system, we do leave out major outer solar system bodies like Pluto, of course, which you can hear about in this week's bonus lecture, Comet 67P, and the Kuiper Belt objects such as the minor planets. But to cover everything, this would have to become a Wagnerian 4-hour-long video, and no one wants that. No one wants Wagner. So with that, let's get into how much we've actually explored in the outer solar system, with what and when. I hope that by this point you know full well that Jupiter is the largest planet in the solar system in both mass and volume. But given how far away it is, how much have we explored it, and just what else do we know about the planet? Well, the first spacecraft to ever collect data on Jupiter was Pioneer 10 in 1972, followed shortly after by Pioneer 11 in 1973. The Pioneer program sent probes throughout the solar system, 8 in total, Pioneer 10 and 11 being the last of them. The big findings from the Pioneer missions at Jupiter were a better understanding of the extent of Jupiter's magnetic field and the fluid nature of its upper atmosphere. By comparison, the images collected by Pioneers in 10 and 11 are not really much better than what you can get with a half-decent backyard telescope today in the 2020s. But in the early 1970s, these images were nearly priceless and far surpassed what 1970s telescopes could do at the time. At the end of the day, the Pioneer missions to the outer solar system were just a step up for the bigger, were just a step towards bigger and better things. From the beginning, they had been designed to test questions about exploring the outer solar system, including navigating the main asteroid belt, something we now know to not really be an issue, as well as, more significantly, questions about communicating with spacecraft that far away, especially given the unknown levels of radiation and magnetic interference that were expected in the Jovian and Saturnian systems. But like we said, Pioneer just gave us just enough answers that the next steps were ready to be taken. With the passage of Pioneers 10 and 11 into the unknown realms beyond the gas giants, the greatest outer solar system mission of all time was ready to make its name known.
1. We have ignition, and we have liftoff. We have liftoff of the Titan Centaur carrying the first of 2 Voyager spacecraft to extend man's senses farther into the solar system than ever before.
The dark room is the center of the universe. It's where we communicate with the deepest spacecraft we have out. We still communicate with the Voyagers. They send us signals every day. You can see Voyager 2 is being tracked both by Antenna 35 and Antenna 36. Voyager has been a real mission of discovery. Every planet we flew by, we got more questions than answers.
I think none of us knew when we launched 40 years ago that anything would be working for such a wonderful long journey. We had hoped that we could reach interstellar space. We reached that with Voyager 1, and we're about to reach it with Voyager 2.
Voyager 1 is the further of the 2 spacecraft, and it's currently at about 13 billion miles from us here on Earth. The transmitters on the Voyager spacecraft are slightly over 20 watts, about what your refrigerator light bulb would give off. So when the signal crosses that vast distance to us, the strength of the signal is 1/10 trillionth of a billionth of a watt, which is the equivalent of 1 divided by 10 with 21 zeros after it.
A real opportunity on Voyager 2, of course, is because we have a working solar wind instrument to measure the solar wind itself. It's currently measuring the solar wind inside the bubble. When it leaves the bubble, it will then enter interstellar space where there's an interstellar wind, which has come from other stars that blew up. And so we will have a chance with that instrument to actually measure the wind for the first time directly. The wonderful thing about the journey is not just that it's 40 years long, but in fact it's still discovering new things because it's going where nothing has been before. They will continue until they finally run out of power, but they will orbit the center of the Milky Way galaxy. For billions of years, are silent ambassadors.
The Voyager program included 2 probes, and while it can sometimes be easy to confuse Voyager and its inner solar system cousin Viking, there are of course major differences. Yes, both were NASA missions from the 1970s that started with the letter V, and yes, both included 2 missions, but that's where the similarities end. The Voyagers were essentially beefed up Mariner probes, who you might remember from Venus and Mars. They were also single spacecraft, so unlike Viking, they had no landers or descent components. They were just big fancy probes that took pictures and measurements of everything they could in the outer solar system. Notably, the Voyagers took advantage of a serendipitous planetary alignment. In the late 1960s, it was noted by astronomers that the outer planets would be mostly on the same side of the solar system for an extended period of time. Hypothetically then, this would allow a single probe to capture data at various distances from each of the 4 gas giants. Remember, this is the 1960s. Humanity is still getting its feet wet in outer space. The gas giants were tens of times further away than the Moon, Venus, and Mars. Other than basic facts garnered from telescopic observations, we knew practically nothing about them. When it came to the questions of satellites or moons, only the largest ones of Jupiter and Saturn were even known. The idea of getting a camera within even a few million kilometers was making planetary scientists salivate. This once-in-a-lifetime planetary alignment needed to be taken advantage of. So, after much debating and budgetary-related arguments, the Voyager program was approved and slated to launch in the late 1970s. It helped that by this time the Pioneer probes had proven that yes, outer solar system exploration was possible. It also helped that the Apollo program and its giant expenditures were over. NASA was being asked to relocate its focus to the outer solar system, as well as the new space shuttle program, and the timing was right for Voyager's Grand Tour, as it would become known. Literally, the planets had aligned. To cover as much of the outer solar system as possible, the two probes were given different paths. Voyager 1 would visit Jupiter, Saturn, then Saturn's moon Titan, while Voyager 2 would visit Jupiter, Saturn, Uranus, and Neptune, making Voyager the first, and so far only, spacecraft to travel near either of the outer two gas giants. At Jupiter, the Voyager probes captured better images of the complex fluid motions of the planet's upper atmosphere. They also confirmed that Jupiter had a ring, not a very large ring like Saturn, but a ring nonetheless around the planet's equator. The ring system at Jupiter would be the first clue to a now known fact. All the gas giants have ring systems around them, perhaps remnants of failed moons, or simply reflective of the more populated outer solar system environments they formed in over 4 billion years ago.
The only thing we can say for sure is that Earth as we know it will be so changed that we would scarcely recognize it as home. But even 1,000 million years from now, something of who we were and the music that we made in that long ago spring will live on. In that distant future, our sun will have completed another 4 orbits around the center of the galaxy. And the Voyagers will have ventured far from the sun. Carl Sagan was a member of Voyager's imaging team, and it was his idea that Voyager take one last picture. A generation before, an astronaut on the last Apollo flight to the moon had taken a picture of the whole Earth, the planet as a world without borders. It became an icon of a new consciousness. Carl realized the next step in this process. He convinced NASA to turn the Voyager 1 camera back towards Earth when the spacecraft went beyond Neptune for one last look homeward at what he called the pale blue dot.
That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust, suspended in a sunbeam. The Earth is a very small stage in a vast cosmic arena. Think of the rivers of blood spilled by all those generals and emperors, so that in glory and triumph they could become the momentary masters of a fraction of a dot. Think of the endless cruelties visited by the inhabitants of one corner of this pixel on the scarcely distinguishable inhabitants of some other corner. How frequent their misunderstandings, how eager they are to kill one another, how fervent their hatreds. Our posturings, our imagined self-importance, the delusion that we have some privileged position in the universe are challenged by this point of pale light. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. The Earth is the only world known so far to harbor life. There is nowhere else at least in the near future, to which our species could migrate. Visit? Yes. Settle? Not yet. Like it or not, for the moment, the Earth is where we make our stand. It has been said that astronomy is a humbling and character-building experience. There is perhaps no better demonstration of the folly of human conceits than this distant image. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known.
As I've mentioned throughout this course, the 1980s were a dark time for space exploration. Sure, there was the space shuttle, but when it came to actually getting out to planets and moons and doing science, space exploration in the 80s kind of sucked. Well, by 1989, with the Berlin Wall coming down and hair metal beginning its descent into oblivion, there was some light at the end of the tunnel. In that year, NASA launched Galileo. And for more on that, let's jump into a conversation I had with Dr. Phil Stuke and Dr. Tanya Harrison on good old Galileo.
All right, is that all the questions?
I see one of your students must be here.
I see that too. Hey, and grades are already in, so that's not sucking up or anything. That's just genuine admiration of my teaching.
Yeah, there you go.
Okay, so I promised Phil 30 minutes for the deep dive, and we're at 35. So only 5 minutes. That's only 1/6 over. That's not too bad. So Phil, take us into the glorious 1990s mission when Friends was the top show on TV and everyone was listening to Ace of Base. Our successful failure at Jupiter.
Okay, well, yeah, let's go on. Galileo was this great Jupiter mission. First, I show a couple of slides very briefly of what went before it. There were two spacecraft called Pioneer 10 and 11, that made a very quick reconnaissance of the Jupiter system, and one of them went on to Saturn as well. Really, that was to show that you could actually get through the asteroid belt safely. These were the first things that ever did. And that you could actually get past the radiation belts of Jupiter safely. And again, they were the first things to do that. And the information they provided was useful for the next probes. And if we go to the next slide, so again, before Galileo, there were the Voyagers. And these did a lot more to really open up the Jupiter system. They showed us so much about what was there. Galileo then was designed to follow on from that. So Voyager, for instance, discovered that there were volcanoes on one of the moons. So Galileo then is going to make repeated observations again and again and again and again, monitoring that activity and looking at it in much more detail. So it was that sort of arrangement. So
is this a plume, Phil?
Yeah. So that picture, that is the discovery image of volcanoes on Io. And it wasn't even taken for scientific purposes. That was a navigation frame. They took that picture basically so that they could see where the moon is relative to the spacecraft as a way of helping to navigate it. They take a lot of pictures like that as they fly through. So you take a picture like that, and then you want to use an automatic routine to fit a circle to it so that you can define where the center of the moon is. And the automatic circle fitting routine didn't work very well because there was a great big lump sticking on the side of it. And their first thought was, oh, that's going to be one of the other moons. Maybe that's Callisto off in the distance. But when you look at where the moons are, there was nothing there. And then they started to realize that this was a volcanic eruption on the moon. With that, I remember that it was several days after the flyby before people figured this out. And it was really a pretty special moment. Yeah, very exciting. And I suppose I could say that the lower left image there, which has a kind of funny sort of heart-shaped pattern on the ground with a dark spot in the middle, that is actually that volcano. So the eruption is coming out of the dark spot in the middle. And it's rising up in the air and then falling down around the outer edges to make that larger loop all around it. Okay, so that was Voyager. Now we go on to Galileo, which is named after this fellow, Galileo himself, who in the very beginning of the 17th century looked at Jupiter with a telescope and saw 4 little spots beside it. And when he looked again, they'd moved a bit. So he realized that they're there with Jupiter. They're moving along with Jupiter in the sky, but they're moving around it as well. The first discovery of any planetary satellite. So the spacecraft named after him. Here it is being launched by a space shuttle, one of 2 planetary probes launched by a space shuttle.
Oh, no, hold on. To Venus.
Magellan was the second. Yeah.
Yep.
Right. That's right.
Yes.
So yeah, here we are, launched on Atlantis. And a lot of people were nervous about that because you can't go from the space shuttle sitting in low Earth orbit to Jupiter without having a great big rocket to push you there. So that's the thing underneath the probe there. The thing with USA written on it is the upper stage rocket. So the space shuttle has to launch basically with many tons of high explosive fuel nestled in its cargo bay. And, you know, it was somewhat nerve-wracking, but of course everything worked fine, and off it went.
Was there any practical reason to do that, or was it entirely political?
Well, it was really political. It was NASA was spending a lot of money to develop the space shuttle, and they wanted to find as many uses for it as they could. And it may indeed have led to the demise of Galileo. We're going to discover shortly that all was not well with the spacecraft, and that's partly because it had been built in JPL and trucked across the country to the Kennedy Space Center, and it was going to be put on a rocket, put into the shuttle and launched. And then there were serious problems, including, of course, the Challenger accident, which delayed flights for quite a while with the shuttle, which basically caused a long delay for Galileo, and it had to be trucked back across the country again and so on. The storage and possibly the transport might have contributed to the fact that its antenna got stuck in an unopened position, which we'll see shortly. It's not necessarily clear that's true, but there was a serious problem with that spacecraft. So let's go on.
It's interesting you mentioned, like, this is a bomb in here.
Yeah.
The shuttle itself, like, this is a giant liquid fuel bomb. These are 2 little missiles. The whole thing was just a gigantic, dangerous system. But yeah, adding another one is an interesting choice.
Okay, so here's a couple of artists' impressions there. Up at the top, you see what Galileo was supposed to look like, and down below what it actually did look like. And basically, they look similar, except for one thing, and that is that there's this big antenna, which was a kind of a wire mesh antenna that is folded up against that central column there, and then it was supposed to open. But some of the ribs that helped to define the shape, some of those ribs got stuck, and you know, the ones at the bottom in the lower image, which haven't moved off of the central support. So half of it was opened and half of it wasn't, and they did everything they could to try to move that, but it never did open. And as a result, they could only transmit a tiny proportion of what they needed to. I'm sure somebody's got a proper number for this, but I would guess that it was far less than 1% of the actual number of bits that they really intended to transmit.
I have it. I was doing research. So the low gain antenna, the small one, could do 8 bits per second. With the large, they were expecting at least in the thousands of bits per second.
Right.
So as Phil will explain, they ended up relying on the small antenna, which is 8 bits per second. So what could have been essentially HD streaming of at least pictures turned into the worst internet connection you could possibly imagine.
That's right. That's right, yeah. And so basically, you have to figure out some way of dealing with that. So one thing is that instead of transmitting images in their highest quality, you transmit very compressed images. And these days, we all get to see that happening with video streaming and so on, when things slow down and they, you know, you're not getting the picture that you want. So they had to compress images. So practically everything that came down was very heavily compressed, as much as they could get away with. And if they needed something that wasn't compressed, there had to be a really good reason for that, you know. So a lot of stuff was very compressed, and they tried all sorts of other tricks as well. For instance, the images were 800 by 800 pixels. So what they would do was they would transmit a very, very condensed version of it. In fact, what they would do is they'd transmit one row of pixels and then another row a bit further over and another row. So they transmit maybe 10 rows of pixels spread across the whole image. And that way you can see whether the target that you want is in it. If you're taking a picture of a moon, is the moon actually in it? And where is it? And once you've found it by looking at those sparse rows, then you can just transmit the little bit that has got the target that you want. So quite a lot of images that came down, all they did was to transmit the little window with the bit of detail they wanted and not the whole image. So there are all sorts of little tricks that they played. But because, although they couldn't get very much back, they chose what they got back very carefully so that they could meet as many of their goals as intended. And they did pretty well with that.
Yeah, and what they ended up doing was they would wait for close passes of one of the moons or Jupiter, take good pictures, store them on what little stores they had, and then while they were waiting for the next close pass, they would do what Phil just said and send what they could back with their really crappy connection. What they would have been doing the whole time is imaging as much as possible.
Oh yeah,
close passes the way orbiters typically do. They ended up having to just be a close pass imager system, which works, but obviously is not ideal.
No, and it's really interesting to compare that with Cassini, which worked perfectly. So Cassini is exactly the same situation. You fly past a bunch of moons and the rings and the planet and so on. You get lots of data and you transmit it back, and then you're going out the rest of the orbit and you can go and look at other things like distant moons or sort of continual monitoring of the Saturnian atmosphere or something like that. With Galileo, they might make a close flyby of one of the moons, but instead of filling the memory with 200 or 300 images and then getting them all back and then taking a whole bunch of other stuff, they might only take 20 pictures in one orbit. And those 20 pictures then took a month to transmit. And you're not doing anything else while you're doing that. So that's the kind of situation they were in. But they did get those 20 pictures, and then you do another orbit. So you just have to pick your images very carefully, and you compress them as much as you can anyway. And, ultimately you make things work.
Yeah, and the last thing I'll say on the high gain antenna that didn't unfurl, they knew that it had partially unfurled. Because there was a solar sensor on board that was being blocked. And they knew the only way that could happen was if the antenna had partly unfurled, because when it was going to unfurl, it was going to block it. And they knew that. So they knew that it had started the process and something got caught, jammed, whatever. And it's kind of heartbreaking. I was reading Jeffrey Kluger's book. It's called Journey Beyond Selene, which is about exploration of all the moons of the solar system. It's already 20 years old now, but he describes the head engineer who knew this system like the back of his hand, and he's just thinking, just like something you built yourself, every little part of it. He's just thinking, what bolt is it? What little screw is it? What is up? And there's nothing you can do. It's 5 acres away at this point.
That's heartbreaking.
Okay, so we'll have to go through this pretty quickly, but basically they looped around the solar system several times. They managed to fly past Venus and the Earth a couple of times, and then a couple of asteroids. So let's go on there. Here we've got an image, infrared image of Venus at the top. So they got some useful data every time they flew past something. The stuff they did for the moon was really quite useful, including these infrared images of the moon. These days we're kind of fairly used to seeing pictures like that, but they were quite innovative for that time. So we got some good stuff anyway. It wasn't just a sort of a useless exercise and flying past Earth to get the gravity assist. You also got some good data. And now let's move on. Here they flew past an asteroid. This was the first asteroid ever visited in space, so it was a real big first for the mission. A little thing called Gaspra. Better go to the next image.
Did you map Gaspra?
Yes, I have a paper on that. Yeah.
Yeah. For those of you who don't know, Phil maps weird shaped things. That's what he's most famous for.
Yeah. So my maps of these things are in the NASA's planetary data system. I did IDA as well. For this one, they flew past IDA and discovered quite by chance that it had a moon. And this was one of these things where they were just transmitting these individual little strips of an image to see which pictures actually had part of IDA in them. And one of those little strips had a funny little blip off the side of the asteroid, little something in it. So they realized there's something else there, and then they get the whole picture, and there's this little moon. And it was completely unexpected. The first asteroid moon ever discovered. We know lots of them now, but this was the first. Really interesting observations. And then this is something it's easy to overlook about Galileo, but it did something quite amazing as well. Back in 1994, a comet which had been captured by Jupiter broke up into multiple pieces, which continued orbiting Jupiter and then struck the surface. And so if you imagine that line of comet fragments zooming in towards Jupiter and hitting it one after another over the course of several days, and each one makes this big dark spot, which you can see in a Hubble telescope picture at the bottom there. Once the comet was discovered, people realized from its trajectory that it was going to hit the planet, and they had months to prepare for it. And the Hubble Space Telescope was available and so on. But Galileo was the only thing that was in the right place to actually see the collisions. The top row of pictures are from Galileo, and you can see a little dot beside them, beside the planet there. It hit on the dark side, and from Earth, you had the view that we have at the bottom there, where you're not actually seeing the dark side. It's almost a full phase. You don't really see the dark side. So the impacts happened in a place that couldn't be seen by Hubble or by ground-based telescopes. Galileo was the only thing that was in the right place to see it. So it took, even though it was far away, but it could get an observation, and you could look at the rise in brightness and then the decay in brightness of the flash and get some information from that. So it was an interesting event.
So this is Galileo's view looking back at Jupiter, and then it sees this flash like a nuclear bomb going off.
Right. Yeah.
Jupiter.
Yeah, and then a bit later on, Hubble takes the image and it can see the debris in the atmosphere of Jupiter there.
Wow.
There's two separate strikes there. Yeah. Okay, so they naturally studied Jupiter itself, so there are quite a lot of pictures of clouds. But this is one of the things that was particularly hit by the antenna problem, because there would have been tens of thousands of pictures like these, tens of thousands, if the mission had gone well. Because when you're close into the planet and you're flying past the moons, you're studying them. But when you pull away and you've transmitted all that stuff, you've got time to look back at the planet and take lots of pictures of it. And that's what Cassini did. But for Jupiter, those images of the planet were basically almost all pushed aside just to slowly transmit all of the other data. So we didn't get anything like the amount of stuff that could have been done, but still quite a lot. Yeah. Okay, let's go on there. The spacecraft carried a probe which was dropped into the atmosphere. It was released, I think about 6 months before the spacecraft arrived at Jupiter. So it released quite early, and it just zoomed in and hit the planet, and the spacecraft then diverted itself so it wouldn't zoom in and hit the planet and went into orbit. And of course served as a relay for the data. And that probe, it entered the atmosphere, it descended on a parachute for about an hour, studying the physics and chemistry of the clouds and transmitting that data back. They didn't find as much water as they expected, and this is something that's only recently been understood, because people thought, well, maybe we just landed in a place that was drier than usual. And now it seems that we understand from a new spacecraft, Juno, that is there, that actually the whole atmosphere tends to be drier, at least the upper atmosphere tends to be drier than we'd anticipated. So maybe Galileo's data were more typical than people had thought at the time. So far, that's the only probe in the atmosphere of one of the outer planets. Now let's have a quick look at the moons. Here's Io. This is the one with the volcanoes. On every orbit, when they could do it, Galileo was able to monitor the volcanoes. That row of pictures at the bottom show the same place, and it's actually that same place that we looked at in one of the earlier Voyager images, with an eruption happening in the dark spot in the middle, and then the stuff sort of goes up in the air and then falls down around it to make the reddish circle. Red is sulfur. But you can see that each picture looks different because there are eruptions going on all the time, and not just from that, but from other ones as well. So you see changes constantly. Yeah, it's a very, very active surface. And we also got infrared images that showed the plumes and hotspots on the surface, lots of them, so we can see some in that picture. And on the right, you can see an image that has another volcano rising above the horizon there into space. Yeah, so that was a significant part of what the mission was all about. But let's move on and look at the other moons here, because they're all interesting. Here's Europa. This is an amazing place. It's a little bit smaller than our moon, but it's covered, and it would be a rocky world inside it, like our moon, although a bit smaller. But it's surrounded by an ocean of water, probably 100 kilometers deep. And on top of that, an icy crust. So the upper part's frozen. And what we're looking at is the fractured ice layer over the top of the moon. So it's just covered with fractures like that. And because there's an ocean, well, it's conceivable that there could be things living in it, or at least biological materials in it. So it's become one of the favored places for people to think about looking for signs of biology in the solar system. Let's go on. Here's a close-up of it. One thing that I always find hard to get my head around is that all those lines are actually ridges. At first I want to say, oh, they're cracks, they're depressions in the surface, but no, they're ridges sticking up. You also get these sort of broad bands. And if you take those broad bands, like the one that runs across the middle of that picture, it looks smooth. It's quite wide. If you take that and you try to, you could imagine cutting out the top part and sliding it over and seeing how it matches up with the part below. And you can actually make things line up really well like that. So it seems that the surface has actually fractured, and the parts have drifted apart like the continents do on Earth. So a very interesting place. And we're not seeing craters. We didn't see craters on Io either, because they're all covered up by volcanic activity. And we're not seeing craters here because the surface is so active, constantly being broken up and things happening to it. So very few craters. But now we'll move on to a place that has a lot more craters. This is Ganymede, the next moon over. And it's the biggest moon in the solar system. It's bigger than the planet Mercury, but a very different looking surface. And again, it's got lots and lots of fractures on it, but there are also quite a lot of craters. So it's an older surface. And really quite a dramatic and interesting place. Yeah, okay. And here's a close-up of Ganymede. And this is another of these places where there's a smooth band. It's brighter this time, running across the center of the image. But the two sides, if you move them together, you can see how they line up. And these haven't just pulled apart; they've also moved sideways. But they actually do line up. And if you do put them back where they belong, then you can see the fractures running across the gap, and even craters that have been cut in half by the fracture, and the two sides separated, and you can actually see how they fit back together again. So again, there's been some sideways movement, like kind of plate tectonics on Earth. Yeah, so an interesting place. The moon, it's the only moon that has its own magnetic field, rather than something just induced by the planet. Oh, and here's Callisto. This is the fourth of these really big moons. And this one really is covered with craters. It's had far less actually happening on it than the other moons. So in a way, it serves like a kind of control for what these kinds of moons would be like. This is almost as big as Ganymede. It's almost as big as the planet Mercury, and just completely covered with craters. The very biggest impacts have smashed into the surface, and it's as if they've kind of sent out ripples into the surface, which have frozen in place. I don't know that that's really exactly how they formed, but it looks a bit like that. Ripple rings around a little smooth patch in the lower right. That's a really... Sorry? No?
No.
You okay?
Gotcha. Yeah.
Oh, okay. There we go. Yeah, and so here's a close-up of Callisto. There are lots of craters in the previous view, and you'd expect to see more here. But what happens when you get really close in is that you find that the surface has been affected by the ice kind of evaporating, or subliming, we should really say, away. The ice just turns into vapor and drifts away, leaving anything that was in the ice, like little bits of meteoric dust and stuff, on the surface. So it has a dark surface, but the surface is gradually evaporating away like that, and it makes it smooth in places, but also it leaves these spiky hills. So I think that this is the kind of thing where you could imagine if you had say a meteorite or something, some rock sitting on the surface, or a block thrown out of a crater, and it kind of protects the surface around it as that's evaporating away. So you get these residual hills.
That's cool. It's kind of like the Callisto version of a glacial
So
erratic, when glaciers leave giant boulders behind when they melt.
We'll wait for Phil to reconnect here, but he's going to jump into these smaller moons, many of which we had no idea existed until Galileo came around. Phil, are you back with us?
Oh, I think I am. It feels like I'm back. Okay. Okay. All right. Yeah. Okay. So there we go. Yeah, lots of little moons. Jupiter has many small moons. Most of them are far out away from the planet, but 4 of them are close in, and this shows some of them. And at the very end of the mission, there was a close flyby of the one called Amalthea, but close-up images were impossible because of radiation dam. That they tried to take them, but it didn't work. Time. Anyway, they had a close flyby. So here we see just a little bit of information about the rings. Yeah. Okay. So yeah, that's it. And that we're losing it. Yeah. Oh, okay. There we are. End of the mission. The spacecraft crashed. His
audio's breaking up, but yeah, when
Galileo nothing went right for it. All right. So at the end of the mission, they just burned up in the atmosphere. The spacecraft did to burn up so that it wouldn't hit one of the moons and contaminate it. But it was a good mission. We just didn't get as much back from it as people would have liked. But still, we learned a lot. And a couple of quick flybys.
Phil's breaking up again, but he's talking about, of course, we did get images of Jupiter
to monitor volcanoes on Io. Now we spacecraft there called, which yeah, there was one infrared image that has lots of volcanoes and hotspots on Io. It's sort of lower center, and the weird thing on the right is an infrared image of the auroras, the Northern Lights, the North Pole of Jupiter.
Oh,
That
Phil.
image looks like the gates to hell or something.
Yeah, that is as you're talking about one of the storms in infrared. Jupiter's a scary place when you look up close. It is quite terrifying, and yeah, in some of these other filters, it looks like hell.
Oh, okay. Are we back?
Yeah,
Oh, yeah.
you dropped.
Yeah. Okay, well, hopefully the images told their own story.
They do. They do.
Danny covered for you really well.
Oh, okay. Well, that's good. Okay, yeah. So it was a good mission, but just didn't give us as much as we would have liked.
I forgot that it lasted for 8 years.
Yeah.
Yeah.
Good. Yeah. Yes, Aurora Borealis of fire, indeed. Yeah. It's quite a dramatic picture.
As you heard there, the follow-up to Galileo was Juno. Juno was launched in 2011 and arrived at Jupiter in 2016 when it entered into a polar orbit above the planet. In this orbit, Juno passes over the North Pole of Jupiter every 53 days. Earth days, that is. A polar orbit is one that is essentially perpendicular to the equator of the planet. When the spacecraft moves through its orbit above the planet revolves underneath, allowing the entire thing to be imaged more easily than if the craft were in an inclined or equatorial orbit. Jupiter's specific science objectives included study Jupiter's deep structure by mapping the planet's gravity field and magnetic field, probe Jupiter's deep atmosphere and measure how much water there is, sample electric fields, plasma waves, and particles around Jupiter, and take images of the atmosphere and auroras, including chemical fingerprints of the gases, using that old friend of ours, spectroscopy. Juno captured a lot of spectacular images of Jupiter in very high definition and was the undisputed desktop background choice for a few years there. The mission also discovered that storms the size of the entire Earth were happening in bunches at the planet's poles. Also, the north and south poles of Jupiter are quite different from one another, a phenomenon that could be seasonal. If it is seasonal, we need to watch Jupiter up close for more than just a few years. Remember that a Jovian year is 12 Earth years. Juno also discovered that Jupiter's magnetic field is far more powerful than previously thought, giving new insights into the size and potential composition of Jupiter's core. Notably, the magnetic field around Jupiter is uneven and shifts depending on where a spacecraft is in its orbit around the planet. Is Jupiter's core uneven, molten, still changing? We're not sure, but there were other findings from Juno as well. So let's hear from NASA's top planetary scientists and members of the Juno team on what is going on at Jupiter.
Hey, this is Dr. Thomas C. with Science in Seconds, and we're celebrating an anniversary today. It's the 9th anniversary of the launch of Juno. And with me here to talk about not only Juno, but 3 new publications that just came out are Scott Bolton, the PI of Juno at Southwest, and Heidi Becker at JPL, who's the lead of the radiation monitoring group. Scott, what's new?
So we've got 3 new papers coming out, and they deal with the topics of lightning. We found some lightning really high up, much higher than we expected. And we've also developed a theory that shows that hail is pretty common from violent thunderstorms at Jupiter, and it's carrying ammonia and water down deep into the atmosphere. And these are really exciting results because most of the weather and meteorology on Jupiter is driven by ammonia and water. And on Earth, it's all driven by water. But on Jupiter, it's a little bit different. Ammonia starts playing a really important role.
So Heidi, talk to us about these hail balls. Like, talk to us, how should we imagine them?
Well, they're very large. They're at least as large as a softball, maybe quite a bit larger than that. And on the inside, they're made from a pretty unusual ammonia water solution. It's kind of like a Windex snow cone, if you can imagine that, covered in a hard water ice crust that gets thicker and thicker and thicker the longer it's tumbled in the atmosphere by Jupiter's violent storms, until they get so heavy that they fall deep into the atmosphere and carry the ammonia down deep.
So Scott, one of the most amazing views, of course, are these images that so many of our citizen scientists worked on, which is this beautiful, highly structured atmosphere, really, of this planet. And I'd like to understand, like, is this structure kind of further in, or is it on the inside? Is it more like, you know, uniform, or you know, how should I think about these kind of weather observations here?
So that's one of Juno's discoveries, is we're seeing that this stuff goes down pretty deep. You know, before Juno, we thought that all those beautiful clouds and zones and belts and the winds on Jupiter were just skin deep, but in fact they go down quite deep. And so what you're seeing at the top cloud layer is really the very top part of a storm that has really deep roots and is violent thunderstorms with lightning and strong winds.
That's amazing. So Heidi, how did you actually discover this? What's the instruments you used for this?
Well, we actually used our engineering star camera to do it. It's there to help us navigate Juno and tell us where we were pointing when we took our data, but it's incredibly sensitive. It can see very dim things, and because Juno flies so close to the cloud tops, we were able to see lightning flashes that were much smaller than any prior mission had ever been able to see.
So Heidi, what's the most exciting part of this discovery for you personally?
Well, for me personally, it's the realization that lightning on Jupiter isn't happening the same way it happens like it does on Earth. That's what everybody thought. Looking at images from back to Voyager 1, everybody thought it's made in the deep water cloud where thunderstorms are like they are at Earth. But these altitudes where we're seeing them happening, these small lightning flashes, it's happening where you can't have liquid water, but there's something special in Jupiter, which is ammonia, and that acts as an antifreeze that allows water ice to melt at those high altitudes and create the conditions for lightning. So it's very exotic and very different than what we have here on Earth, and that's what's most exciting to me.
Scott, Heidi, this is just an amazing discovery, and I just want to congratulate both you and the entire team for this amazing work during the last 9 years and also for the years to come as we observe the amazing hurricane on the East Coast that just went over our house here. Of course, it's just amazing to think that out there in the solitude of space where Juno makes observations, there is violent weather of type that we've never observed here, and that's exactly why we do these amazing missions, is to learn about nature itself in other places. So thanks to you and congrats.
So what's next for the Jupiter system? The answer is JUICE, that is the Jupiter Icy Moons Explorer, which will be led by the European Space Agency and launched in 2023, hopefully. JUICE will mostly ignore the giant planet taking up most of the Jovian system and will instead focus on the 3 moons of Ganymede, Callisto, and Europa, which, as you may recall, are all moons thought to have icy crusts covering subsurface oceans of water. The main objectives of JUICE will be to characterize the ocean layers and detect subsurface water reservoirs, undertake topographical, geological, and composition mapping of the surface, study the physical properties of icy crusts, characterize internal mass distributions, dynamics, and evolution of interiors, investigate Ganymede's tenuous atmosphere, and study Ganymede's magnetic field and its interactions with the Jovian magnetosphere. Once all this is done, JUICE will take a collision course to Ganymede and end its mission in a blaze of glory like Cassini before it, by crashing into something for the sake of knowledge. Speaking of Cassini, after this short video about JUICE, let's head out to Saturn.
In Roman mythology, Jupiter was seen as the god of the sky, and it is, kind of. The biggest celestial body in the solar system has all the characteristics to be a king of our planetary system. The ESA's mission, JUICE, will provide the most comprehensive exploration of this giant planet and in particular of its moons, supposedly hiding habitable zones under their icy crusts.
Jupiter is a gaseous planet, meaning that if you try to descend into Jupiter's atmosphere, you wouldn't encounter, as on a terrestrial planet, a solid surface. Rather, you'd be in an increasingly thickening fluid.
What's intriguing for the astronomers is the specificity of the Jupiter satellite system. and the vast oceans of liquid water underneath some of its moon's surfaces.
Jupiter itself is like a real planetary system with many satellites, in particular the 4 discovered by Galileo a little more than 4 centuries ago. These satellites are a world apart, each of them with a different geology. The mission JUICE will study them, at least the 3 furthest from Jupiter.
If the Jovian system can be seen as its own solar system to scale, Jupiter has missed its chance of being a shining star.
We refer to Jupiter as a missed or failed star because Jupiter is an intermediary between the Earth and the stars. She does not have sufficient mass to trigger the thermonuclear reactions that give a star its energy. She has hydrogen, but not sufficient temperatures to radiate like a star.
Understanding the Jovian system and its history, according to the JUICE project scientist Olivia Vittas, will give us better insights on how gas giant planets and their satellites form and evolve.
Jupiter is a planet of superlatives. It's the largest planet in the solar system, the biggest storm of the solar system, the largest moon system, after Saturn's, and the largest magnetic field.
During its 3.5-year mission, JUICE will travel around the giant planet, studying its atmosphere and 3 of its planet-sized satellites, Ganymede, Europa, and Callisto.
If we find some oceans on Jupiter's moons, we'll be able to study if there are habitable environments that could harbour life.
Ahead of this, it will be necessary to travel through the solar system for nearly 8 years, and first of all, to safely exit Earth's gravity. This is one of the most risky moments in a space mission.
For me, the blastoff phase is the most critical one. We have to trust the launcher, which must be able to get away from the Earth's gravity and drive us on the right trajectory. At the end of the mission, we will put JUICE into orbit for the first time around one of the moons of Jupiter, Ganymede, the largest moon, and again, putting a satellite in orbit around a moon is something critical.
JUICE will perform several flybys of 3 of Jupiter's 4 main moons in order to unlock the secrets of the potential habitability of an outer solar system.
Europa and Ganymede are very, very big examples of the possibility of liquid water underneath the surface. The only thing that remains for us to find is how this water, how deep is it, how far is it from the surface, what its extent, and if there could be life, living organisms originating in the liquid water within the underneath oceans on these icy moons.
JUICE will spend the main part of the mission around Ganymede, one of only 3 solid bodies in the solar system with a magnetic field.
Ganymede has the magnetic field, and it is the largest satellite. If it possesses also liquid water underneath its surface, it is the place to go to look for life conditions, habitable conditions in the solar system besides our own planet.
This space mission requires years of patient work in dealing with the limits of our technology, which will be nearly out of date when the space probe begins sending back its first data. It'll be like receiving a call from the future.
A space mission is nearly a lifetime project, and we must be patient because data returns in a far distant time, 20 years or 25 years for some missions. By studying Jupiter more closely, we have access to some physical mechanisms which play a role in other planetary systems, which we hope will lead to a better understanding of exoplanetary systems.
Every space mission we make produces data for generations of astronomers to be working on them, as I did myself. And I'm hoping a lot of young people will now think about working on JUICE data decades from now.
All right, well, it's time to move on from Jupiter and out to Saturn, the one with the big rings. The history of exploration at Saturn is pretty similar to Jupiter. Pioneer and Voyager came first, but instead of Galileo, Saturn got Cassini, a different old dead scientist. And since then, not much really. But Cassini was so successful it left us with more than enough data until eventually a mission to Titan gets going called Dragonfly. We'll hear a little bit more about that in a second. Let's jump over Pioneer. While it did provide critical early images of Saturn, it can be ignored otherwise. Sorry, Pioneer. As for the Voyagers, they both visited Saturn in the early 1980s. They confirmed that the ring system was complex and evolving, and Voyager 1 tried to glance at Titan but couldn't see past the moon's thick orange layer of clouds. Titan would remain a bit more of a mystery for another few decades until the Cassini mission. Since Cassini was such a long and successful mission, I'm going to hand this over to someone with a little bit more experience than me, the original space professor, again, Dr. Phil Stuke.
All right. So now I guess we'll move on and look at Cassini. So I remember once in a planet club or space club at Western that we were talking about favorite missions. And I think several people said that Cassini was their favorite mission. And I said, well, for me, it was Voyager. But that shows how old I am, because you had to be there, right? So for me, Voyager was fantastic because it was the first time that we really got to understand what the outer solar system was like. But when we look at the Voyager images now, compared with what we had from Galileo and then from Cassini, it's really incredible how much better things are from these newer missions. So Cassini was fantastic just because there's so many targets. Like I say here, the planet has it all. You've got the planet itself with its atmosphere and all sorts of things around the planet itself, its magnetic field and so on. You've got a giant ring system, lots of moons, and the moons are incredibly varied. And we'll see some pictures of them. And a couple that are really amazing, Titan and Enceladus there, which we'll look at. Hey, Titan number 1. Hello, Ian. There you go. Yeah, great. So
there we go.
All right, there's the spacecraft, and just a quick timeline. I'm not going to read through the whole thing there, but you can see that it was actually launched in 1997, and the mission ended in 2017. So that's 20 years of solid exploration that they were doing there. They flew past Jupiter for a gravity assist. They got to Saturn in 2004, and so they spent 13 years, which is about half of a Saturn year, orbiting Saturn and studying it. And there's that amazing spacecraft that did all that stuff. Okay, let's move on there. And it wasn't just the Cassini spacecraft, it carried a passenger, the Huygens probe, which was from the European Space Agency, and it landed on Titan. It parachuted down through the thick atmosphere of Titan, Titan being the only moon in the solar system that has a thick atmosphere. And this probe parachuted down, taking pictures on the way down, and there's a few of them. And when I first saw that picture, it was during a kind of webcast of a landing event at the European Space Agency, and it just appeared up on a monitor on the wall while somebody was talking. And I looked at it and I thought, oh, that must be one of the test images from the Arizona desert that they did when they were, testing the camera before launch. I didn't really think that that's what we were going to see, these kind of dendritic channel structures. But there we are, dried up riverbeds on Titan. Okay, and let's go to the next one. And when they got to the surface, we saw this. There was actually just one camera with a narrow field of view as it came down.
Again.
Uh-oh.
Is he frozen?
We've got robot voice going on.
Okay.
Phil, I'm not sure if you can hear us. If you can, we can't hear you.
In the meantime, so this image is taken from the surface of Titan, obviously. So this would have been from the Huygens probe, which was launched with Cassini with the objective of landing on the surface of Titan. At that time, 2005, the surfaces we had been on would have been Venus, Moon, Mars, and that's it. So it would have been pre.
All right.
Oh, he's back.
Back again.
So I was just
Oh,
highlighting that.
Like everybody was done. Maybe it was only me. Okay, so there we are. Anyway, okay, let's move on and look at some more. Oh no. Hey. Okay. Yeah, so of course the spacecraft monitors the atmosphere of Saturn, which is very active. There's a giant storm that appeared in the northern hemisphere and gradually got stretched out around the planet by the winds. But that kind of atmospheric monitoring went on for half a Saturn year, 13 Earth years, so a substantial amount of time. And one thing that affects the atmosphere of Saturn, unlike any other planet, is the presence of the shadow of the rings. And you can get a sense from that picture that somewhere in the southern hemisphere there below the rings, that the atmosphere would be cooler because it's shadowed. And those shadows, they can move much further south, and then they can flip into the northern hemisphere and be much further north, constantly changing as the seasons progress on Saturn, as seasons like we do. So we got to monitor all of those changes for a long time, and that was great. Let's move on there.
So actually, Robbie's got a point about the surface image.
Yes, they are really rounded, and it's possible that that's because all of those channels that we see mean that there is fluid flowing on the surface. It's not water, though. There is water in that view, but it's the rocks, right? They're ice. The land masses on Titan, if you like to call them that, are ice, and any liquid that's flowing is liquid methane. But it could flow and it could roll over the surface and it could round those pebbles. All right, and then of course there's the rings. The rings are amazingly dynamic as well, and I'm only showing a couple here, special pictures of the rings that were taken when the sun was almost in the plane of the rings. So any little irregularity in the rings would cast a shadow, and we see that there are a lot of those things. The little image on the left shows a small moon casting its shadow across the ring system, a small moon that actually is orbiting inside a little gap in the rings. So very, very interesting world with these dynamic rings. And we might learn quite a lot about other disks from those rings, including things like the very early solar system as the planets were forming in a great big cloud of dust and gas, with the dust forming a ring system around the sun as the planets are gradually forming. So, we might learn something from these rings about other kinds of disks as well.
Yeah, and
okay.
like these. Oh, I think I get an echo off of Phil. I think the existence of these little moonlets in Saturn's ring system and just the dynamism of the ring system as a whole. Like, system's the right word. There's formation of these little moons. There's evidence of them breaking apart. But like, even looking right here, this moonlet forms and it starts clearing a path through. You also have instances where these moons are not on the same plane. So they're a little bit off just by a bit. So they pull the ring up and down towards it as it kind of passes through. So you get these kind of fluttering in Saturn's rings, which you can see, I think, a little bit of here as well. And you had this, also this propeller phenomenon where you get like these waving rings and different shadows coming off of them. So Saturn's rings, which from like Voyager look uniform and simple, and I don't know to what extent astronomers were expecting dynamism or activity, Cassini really showed that if we come back in 30 years and look at the rings, they might not be completely different, but they'll be significantly different, which is really cool to see. Like, not just is the atmosphere changing, Saturn has an entire rock system around it that's changing. I think Phil froze again, possibly.
Oh, yeah, it's not letting me unmute him.
There you go. Okay.
There we go. I just had him muted to get.
Okay. Here's a great picture. Yeah.
Yeah, I took this myself. I processed it using.
Oh, very nice.
So you could probably explain this way better than me, but I call this picture a bit of a mindfuck because making sense of it from an initial viewing is difficult. I found it difficult, and you actually had this at an old space club at Western, and I think you asked us like, what do you think is happening here? So Phil, could you explain?
All right, so now the sun ought to be in that picture, but it's behind Saturn, so we can't see the sun at all. The spacecraft is in eclipse, basically in the shadow of Saturn. Looking back at Saturn, some of the sunlight filters through the rings, so we can see that even though we're looking at the underside, the shaded underside of the rings, but some light filters through. And where the rings are darkest, kind of in the middle of the ring system, that's where the rings are thicker, so less light filters through. That's the B ring. And then Saturn itself ought to be completely invisible because we're looking at the shadow, except that some light from the left and the right sides of the rings is reflected onto the planet. So we're seeing the planet illuminated by light reflected off the rings. And down at right at the bottom is a very faint arc, kind of slightly bluish in that image, which would be the E ring, a very faint outer ring. Yeah, running across there. So all backlit.
The E ring will come back in Tanya's pick, but yeah. So the image is Cassini is looking at Saturn, and the sun's on the other side. So typically you shouldn't be able to see anything, but because the rings act as like a mirror, you get this really strange, what I call the baseball cap image of Saturn, where it's like it looks like it's wearing a backwards hat. And yeah, you're getting a perspective of the far side of Saturn from the perspective of Earth and the sun.
Yeah, great.
That's very cool.
Okay, and then there's the fabulous Titan, the only moon with a thick atmosphere in our solar system. So superficially Earth-like in some ways, but really very un-Earth-like. These are just pictures that show what it looks like if it's your eye at the top. And then with infrared vision at the bottom, a couple of different views. So there are certainly things to look at on that surface. Let's go a little bit closer here, the next picture. And so visual and infrared imaging shows us some things, but Cassini also had a radar, and that can penetrate right through the clouds and haze and see what's on the surface. At the top, we're seeing dark linear sand dunes near the equator, and at the bottom, lakes. The dark stuff is liquid, and dried up river channels, and maybe some of them aren't dry, I'm not sure, flowing into those lakes, and that's near the North Pole. So a very varied surface. Okay, but there are lots of moons, and they're amazingly diverse. So here we've got 3 of them, a couple of them with lots of craters, one of them with a very, very rugged surface, and another one that is so smooth that you can't even see any craters on it. There's some very faint little dark markings, but you can see they're extraordinarily varied, and of course very varied in size. That little one, Methone, is only 3 kilometers across, and the big one, Hyperion, the other two, 300 and 400 kilometers across. So a huge variation, but the moons are not at all what you would necessarily expect to begin with. Especially that very, very smooth little thing, very peculiar object.
Yeah, and well, Mimas, so that I assume is a complex crater with like a central uplift.
Yeah, that's right.
That big of an object, why didn't it just destroy Mimas?
People often say that, but it takes a lot more energy to destroy a world than you might think. I mean, basically, something hit Mimas there. Something hit Mimas, and a shockwave spreads out and digs that crater. But as the shockwave spreads out, it gets weaker and weaker. And when it can't dig a crater anymore, you stop. Well, if you want to destroy Mimas, you've got to have such a big impact that that shockwave spreads through the whole body. So it's going to be a lot bigger than the thing that made that crater. So.
Okay. I buy it.
Okay, let's move on. Here's a couple of nice round ones. They might be round, but they're still doing interesting things. Dione has all these cracks on the surface, and Iapetus at the bottom has very dark patches and light patches. It has a very peculiar ridge running right around the equator for about 3/4 of its circumference, which is just faintly visible at the right-hand edge of that picture. A very peculiar world anyway. So some of them look like that, but now let's have a look at the next set. Others are really bizarre shapes. Look at these strange objects. Pan at the top kind of has a belt of material all around it. That's around its equator. That's the moon that is embedded in the rings. And so material is probably precipitated out from the rings to build up that strange belt around its equator. But a very peculiar looking object. And some are extremely elongated, like Prometheus at bottom left there, 135 kilometers long, but it's only about 40 kilometers across around the middle. So very elongated, like a shard maybe of a larger object that's been broken.
Is there any estimate on how steep the sides are of that equatorial ravioli bit on Pan?
Well, we do have stereo images of that, so that information would be available, but I don't know what the answer is to that. Yeah, it's a very interesting object. And here's Tanya's pick, a great picture of the E ring, which surrounds the main rings. It's further out than the main rings that you see, and it's really very faint, so you really have to take a long exposure picture or crank up the contrast to see something. But right in the middle, there's a funny little thing, which is actually the moon Enceladus, which we're going to look at in a moment, which is a nice little moon, 500 kilometers across, that is blasting out jets of water vapor from its south pole, and that the water vapor kind of crystallizes, and the ice crystals form this giant ring. So a tiny little moon blowing stuff out from cracks in its south pole builds up a ring around an entire giant planet. Quite an amazing thing.
It's worth noting here, the bright spot that you see in that ring there, that's not Enceladus. Enceladus is the dark spot, and the bright spot is all of the stuff coming out of the geysers that are making this ring, which blows my mind.
Yeah.
Yeah, so okay, yeah, it's a lot smaller, okay.
Yeah.
Yeah, it's small.
This is why I really want to see a mission to Enceladus, because literally spewing out of an ocean into space. You know, Europa's cool too, I guess, but I think Enceladus is cooler.
Yeah, we may get to see that. Okay, let's move on to the next picture. Here's Enceladus closer up. The surface has a few craters on it that you can see here and there, especially on the right-hand side there. But most of it is very much broken up. It's been fractured. Pieces have moved around. It's a very strange-looking object. It's clearly been very active. And at the bottom, we can see some of those jets of water vapor escaping from cracks at the south pole of the moon. So really quite a dramatic object. And this is a close-up showing those cracks that are producing those jets. When you look down on them like this, the jets are faint against the illuminated surface of the moon. So we can't see the jets there, but they would actually be blowing right up out of the surface when that picture is taken. It's just that we can't see them in that view. But the view at the top left there shows the jets coming out of the South Pole. And there is a thought that a future mission might be able to fly through those jets and collect samples of them for analysis.
It's kind of interesting, like from bird's eye view of the features giving off the jets, they're not really that remarkable. Like there's no obvious geyser sitting there that looks really, really cool. I guess it also has to do with resolution. But I would have expected to see something more dynamic and interesting, but it just kind of looks like the rest of the planet.
Well, it's because they're faint. So in an image like that one at the top, I think we're seeing them because they're silhouetted against the blackness of space, and they've probably been brightened anyway to make them more visible. But when you're looking down on them against that very bright background of the surface of the moon, they just don't show up. And there's that spacecraft. There's a little person down at the bottom of it that shows how big the spacecraft is. It's kind of the size of a bus, a big thing. And it's still amazing to me that we can build something like that And people, spend a decade or more building a spacecraft like that and more time planning it. And they build it and they trust it to a giant rocket, put it on top of the rocket, fire it off into space, and it can do these amazing things. It's really, just about the best that humans are capable of.
Indeed, the Cassini mission has left a large legacy to live up to, but NASA has something up its sleeve. That's Dragonfly. Now, the Dragonfly mission won't visit Saturn at all, but focus instead on Titan, something many people in the planetary science community have long begged for. Dragonfly will be the first flying mission of its kind. Of course, over the past couple of years, NASA has gained experience flying a craft on Mars with the Ingenuity helicopter, but Dragonfly will be the first time an entire mission's operations are based on a flying asset. Dragonfly will take advantage of Titan's thick atmosphere, something that should make flight relatively easier, and certainly much easier than on Mars, where the atmosphere is wafer thin. Overall, Dragonfly will analyze via direct contact Titan atmosphere and also look for areas on the surface where liquids may be pooling, allowing for rich organic materials of the moon to possibly be incubating life, or at least life-favorable conditions. Whether or not we find these, who knows?
NASA is pushing the boundaries of human knowledge and expanding the limits of technology. I am proud to announce that our next New Frontiers mission, Dragonfly, will explore Saturn's largest moon, Titan. Dragonfly will be the first drone lander with the capability to fly over 100 miles through Titan's thick atmosphere. Titan is unlike any other place in our solar system and the most comparable to early Earth. The instruments on board will help us investigate organic chemistry and search for chemical signatures of past or even present life.
So we have on Titan opportunity to observe the processes that were present on early Earth when life began to form, and possibly even conditions that may be able to harbor life today.
One of the things that is particularly exciting about this mission is that we can do the very detailed chemical measurements, but be able to put them in the context of Titan as a system.
It's the science that really motivates us to do this exciting and difficult mission. Go Dragonfly.
Well, 2 down, 2 to go. And here we have the Uranus. Only ever visited by Voyager 2, at Uranus, Voyager 2 was able to detect the magnetic field of the planet and image the atmosphere in far better detail than anything before. Of course, those were the first direct measurements of the magnetic environment in the outer solar system. Perhaps a bit surprisingly, the planet appeared almost homogeneous in its coloring. It was just blue. There was really little else that the instruments on Voyager 2 could pick up. Now, what were those instruments, you ask? Well, maybe I should have covered this earlier. Among Voyager's instrument suite was, of course, an optical imager, or really just a camera that captured light in the visible red, blue, green wavelengths. Voyager also had a radio instrument that used radio waves to measure the intensity or extent of ionospheres, magnetospheres, and gravity fields around the various objects it encountered. It also had spectrometers, i.e. fancy cameras that capture different wavelengths than the ones our eyes can see. Capturing infrared and ultraviolet light, it had specific spectrometers, as well as a magnetometer for measuring magnetic interference around certain objects. It also had instruments for measuring cosmic rays and plasma in order to understand the radiation of the sun in the outer solar system, as well as the radiation coming off the planets themselves. There were a few other niche instruments, mostly to do with astronomy, but those were the big ones, especially when talking about planetary science. So all in all, both Voyager probes had pretty much everything they needed to tell us what the gas giants looked like up close, what they might be made out of, and how strong the radiation and gravity around them was. Speaking of that infrared spectrometer though, that was the instrument that provided one last finding at Uranus that I want to mention. Based on Voyager's data, the upper levels of Uranus' atmosphere appeared to be roughly the same temperature globally, meaning that there was no internal heat sources that might be isolated to particular regions, nor that the orientation of the planet and its movements in its orbit had much of an effect on the outwards temperature, or the top level temperature of the planet. This is a bit weird.
First detected in 1781 by English astronomer Sir William Herschel, Uranus, in Greek mythology, is the name for the heavens. 5 years and almost 1 billion miles after leaving Saturn, Voyager 2 reached Uranus in January of 1986. Like all the other planets, Uranus spins like a top, but tipped over on its side. Strangely tilted and off-center, Uranus's magnetic field extends in a bizarre corkscrew tail millions of miles into space. Its magnetic poles are also wildly askew. Voyager 2 discovered 2 new rings. Dark, narrow, thin bands of ice, rock, and dust with particles the size of a fist. Although Voyager 2 discovered 10 new Uranian moons, the most eagerly anticipated event was the close encounter with Miranda, one of the most bizarre moons in our solar system. Close-ups of Miranda revealed a strange and wondrous landscape, including a canyon 12 miles deep. Miranda may have collided with another moon, shattered, and then by the force of its own gravity, slowly reassembled itself into this chunk of rock and ice. These digitized photographs are a silent testament to the violent origins of our solar system.
Like Uranus, Neptune has only ever been visited once by Voyager 2 in 1989. With its one pass, Voyager 2 was able to identify that Neptune probably has more methane than the other gas giants, something confirmed by the JWST telescope in 2022. Voyager also identified Neptune's ring system, which JWST has also confirmed, even providing much clearer images of the rings and indicating their almost Saturn-like appearance. If you haven't seen them, I highly suggest you seek out the JWST telescope images of Neptune. They are something. The last major Voyager 2 discovery at Neptune was that its backwards moving moon Triton may be volcanically active. This would be cryovolcanism, a kind of geological activity common in the outer solar system that sees ice take the place of magma. Not much else is known about Triton, but it remains one of the more intriguing mysteries of the entire solar system.
Approaching Neptune, after 12 years on the road and another 1 billion miles, Voyager 2 was an exhausted traveler. By August of 1989, Voyager 2 was speeding more than 40,000 miles per hour toward its rendezvous with Neptune, the last stop on its spectacular grand tour of the 4 outer planets. Discovered in 1846, Neptune was named after the mythical Roman god of the sea. The planet appears blue because its methane absorbs most of the red in the spectrum, leaving mostly green and blue. Voyager 2 flew by Neptune only 22 miles off its charted course, and only 1 second off its scheduled flyby time. Skimming only 3,000 miles over the planet's north pole, Voyager found Neptune to be a giant ball of melted rock and ice, cloaked in hydrogen, helium, and methane gases, its atmosphere whipped by winds of up to 700 miles per hour. Voyager flew the closest that any spacecraft has come to one of the outer planets, discovering at least 4 complete rings of ice and rock, 6 new moons, and a great dark spot, a hurricane the size of Earth raging in Neptune's southern hemisphere. Dr. Andrew Ingersoll.
The storm revolves around the planet every 18 hours, and then it rotates around its own axis like a big glob of pizza dough every 16 days.
Largest of Neptune's 8 moons, Triton orbits in an opposite rotation from the planet. Triton was once probably an independent object in orbit around the Sun, until it collided with a moon and was captured by Neptune's gravity. Pockmarked by impact craters and glazed pink by a radiation blitz of methane and nitrogen ices and atmosphere, Triton is the coldest known object in the solar system and one of the most reflective. Utilizing Voyager's digitized photographs of this icy moon, scientists saw jagged mountains, high cliffs, and frozen lakes. The most bizarre discovery on Triton was the presence of icy geysers, some of which are still active, spewing organic particles 100 miles downwind. Dr. Edward Stone.
The Voyager mission to the outer planets has certainly been a journey of a lifetime. having encountered Triton as the last world we would visit, I don't see how any of the scientists could have been happier.
Voyager 2 has set its course for southwest of the constellation Sagittarius. Traveling at 10 miles per second, it is expected to pass 4 light years from Sirius, the brightest star in the heavens, 290,000 years from now.
Well, there we have it, the outer solar system and all its mysterious vast distances glory. If you have any other questions, don't hesitate to shoot me an email. I hope this discussion has provided you with a lot of mental fodder and has also answered as many questions as it might have provoked. What is certain is that much more about the outer solar system will be answered in your lifetimes, adding to the relatively limited scope of our knowledge when it comes to Uranus and Neptune, as well as what exactly lies beyond them, is to me one of the most exciting things to look forward to in all of space exploration. Until next week, take care.